Hey guys, this is Professor Janacek, and I want to go over how to determine the area under a curve. We're going to start by looking at the function f of x is equal to x squared. You'll notice I'm going to look at it in three situations, but for each one of these I've graphed that curve just from 0 to 4 along the x-axis. So that's the curve f of x is equal to x squared. Now what we're going to do in order to find this area is to approximate it by drawing rectangles underneath that curve or in relationship to that curve. You'll notice that in this situation I am using rectangles that all have the same width. You could technically use different widths, but to make life easier I am going to have them all the same width. So I go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on and so forth. I am also just looking at the area from 0 to 4. We could definitely extend beyond that, but again, I just want to make sure you understand what's going on. If you understand what's going on from 0 to 4, you understand the rest of it. Now let's take a look at when we use the left-hand endpoint. What I mean by that is that I'm going to say, let's take a look at the interval from 2 to 3. I'm going to take a look at the left-hand side of that that rectangle. That's going to determine where I touch the curve, and then off of that curve I can see how high that rectangle ends up being. So again, just looking at one little rectangle, I take the left-hand endpoint to determine where I'm going to go on the curve. Now for the right-hand endpoint, again, looking at the interval from 2 to 3, I'm going to start with 3, and that's going to tell me how high to go, and I'm going to build my rectangle off of that. So you'll notice the left-hand endpoint has a much smaller rectangle, and the right-hand endpoint has a much higher endpoint. This is true if I'm looking at an increasing function. If I'm looking at a decreasing function, this would actually be reversed. And then the final case is where I look at taking a midpoint. So again, for the interval from 2 to 3, I'm going to take a look right there in the middle and see where it touches my the curve. And that's going to tell me how high to go to build that rectangle. So for each interval, I could take either the left-hand endpoint, the right-hand endpoint, or the midpoint. Again, I could do each interval or each rectangle differently, but to make life easier, I'm going to just go with all of them in the same way for each situation. So let's first take a look at the left-hand endpoint. Let's see if we can approximate this area. Remember, for the area, we're going to look at just the area of each rectangle. Of course, the area of a rectangle, we often remember it as length times width. In this case, my length will actually be the height, and the width, so the length will be the vertical distance, and the width will be the horizontal distance. All right, so using the left-hand endpoint, what we end up doing for each little rectangle, let me first look at this rectangle from 0 to 1. How high is that? Well, it's actually, since I'm taking the left-hand endpoint, it touches the curve at 0, so it has a height of 0. And then its width is 1. In the next interval, the height, how high does it go? Well, at 1, 1 squared, of course I'm using my function here, 1 squared is 1, so it's got a height of 1 and a width of 1. In the next interval, my left-hand endpoint is 2. Where does that meet my curve? Well, 2 squared is 4, again following my function. And then the height is 2, the length is again, or the width is again 1. And then the last one, we have a height of 3 squared and a width of 1. oops, those are squares. 0 squared, 1 squared, 2 squared, 3 squared, times 1. So that gives us 0 times 1 plus 1 times 1 plus 4 times 1 plus 9 times 1. Do all of that math, and it looks like we get 14. All right, so that would be an approximation for the area using the left-hand endpoint. Using the right-hand endpoint, now when I look at this first rectangle, the right-hand side is at 1, so its height now is at 1. So now the height is 1 squared. Again, the width is 1 again. For the next one, my right-hand side of this rectangle is at 2. So that height, again, following my function, is 2 squared. And the width is 1. The next interval, looking at the right-hand side of that, I'm going with 3 squared for the height and 1 for the width. And finally, the last one is way out here at 4. Again, the height is 4 squared off of my function. And the width again is 1. So we have 1 times 1 plus 4 times 1 plus 9 times 1 plus 16 times 1, which gives us, looks like that's 30. All right, again, not a bad approximation. You'll notice, though, there is quite a difference between these two. The left-hand endpoint, if I'm using the left-hand endpoint, because my function is increasing, I'm losing a whole bunch. Look at all those big gaps up there. And with the right-hand endpoint, I have all these overages. Look at all this extra on top. Again, this is true only if I'm looking at an increasing function. A decreasing function, these would actually be reversed. I would have too much for the left-hand endpoint and not enough, too little on the right-hand endpoint. Let's now take a look at the midpoint. So for the area, if I take a look at the midpoint, so between 0 and 1, I'm going to figure out what that height is. Well, remember that's 0.5 or 1/2, and then figuring out its height, of course, based off my function again, up there. This gives us 1/2 squared, and then the width again is 1. Plus, in the next interval, between 1 and 2, the height is 1.5. Square that, gives us the height. And then the width, again, is 1. The next one, halfway between 2 and 3, gives me the height of those rectangles. So that would be 2.5. To find the height, though, of course, we square that, and the width is 1. And finally, the last one, halfway between 3 and 4, gives us 3.5. That tells us the height. We square that, and then the width is 1. So what is that? 1/4 times 1. 9/4 times 1 plus 25/4 times 1 plus 49/4 times 1. And in this one, let's see, we end up with what is that? 7. think that divide that by 4 gives us 21. So kind of right there in the middle of the two. And you'll notice this is actually not a bad approximation. We find that we kind of like using this one because we have a little that's under and a little that's over, and they kind of balance out. So that's actually a really nice way to go about finding these areas. So looking at kind of how we set all of these up, they all kind of follow the same pattern. What we ended up doing, you'll notice I have here, I've marked out my first point, x0 is 0, x1 is 1, x2 is 2, x3 is 3, and x4 is 4. So if we want to go with the midpoint, let's just list out what those midpoints are. We'll call them x, the midpoint in the first section is x sub 1, but I'll call it a star to identify it's the x that we're going to choose within that interval. So x sub 1 star, what we end up doing is we take halfway between x0 and x1. Well, a midpoint is adding the 2 and dividing by 2. X sub 2 star is going to be halfway between x1 and x2. So x2 plus x1 divided by 2. The point that we'll select in the third section, the third interval, x sub 3 star, means that we take x sub 3 plus x sub 2 and divide by 2. And then finally, in our last interval, it's halfway between x sub 4 and x sub 3. We could actually compute these. We end up with 1/2 for x1, 3/2 for x2. Oh, these all have stars on them. So x1 stars, 1/2, x2 stars, 3/2, x3 star is 5/2, and x4 star is 7/2. Now to find our area, what we're doing is we are, again, this is technically an approximation. What we're doing is we're taking f sub x sub 1, f of x sub 1 star times, that's the height. Now the width of that is just x1 minus x0 plus f of x sub 2 star, and then it's x2 minus x1. That's the width of the next interval. Plus f of x sub 3 star, and then the width of that interval is x3 minus x2, and finally f of x sub 4 star times x4 minus x3. So what we're getting for each one of these is the height times the width. We could actually rewrite this as the summation instead of writing all of those terms. This is the sum. This k goes from 1 to 4 of f of x sub k star times, now this width we call delta x sub k. So remember delta x, if you remember that notation, this is the change in the x values. All right, now what we'll typically do is we will let all of these delta x sub k's all be the same value, delta x. In fact, the easiest way to do this is to take all the interval. And so in this case, our interval goes from A to B. So A is x0, B is x4. So take that whole distance and divide it by n, and do this for all k. So each interval is the same width, and this gives us the width as long as I have n subintervals. So in this case, I would have 4 subintervals. And the way, again, if you took 4 minus 0, and divided by n, in this case n is 4, you would get 1. So our intervals here in this situation, delta x sub k is going to equal to delta x, which is 4 minus 0 divided by 4, or 1. So the width is 1. And again, this is a nice way of determining the width of n subintervals. I also want to point out that when doing these, finding that x value, what x value you're going to use, this x star, right? How do we pick those? Well, again, we like to pick them the same way. If we're using the midpoint, the x sub k star has the form a plus k minus 1/2 delta x. What you're doing is you're starting with the a value, and then you're going to add just half of, that's k minus 1/2, half of a delta x, half of a width for each subinterval. The right-hand endpoint, the x sub k stars, have the form a plus k delta x, meaning that to get to the right-hand endpoint, for each one, I'm going to add an entire delta x. So if I'm starting at the first interval, I go all the way to the right, add a whole delta x. And then for the left-hand endpoint, the x sub k stars have the form a plus k minus 1 times delta x, meaning to get to the left-hand endpoint, I'm going to go back 1 whole delta x. So rather than going forward 1 whole delta x, I'm going to go back 1 whole delta x. All right, so where does this lead us? Well, here we are. We have an idea of what the area formula looks like, at least when we're going from 1 to 4. But wouldn't it be better, rather than splitting it into 4 pieces, because yes, 4 pieces was nice, but wouldn't it be nice if I can maybe split it into, I don't know, 8 pieces, or split those? And of course, wouldn't it be great if I could split this into infinitely many pieces? Well, of course we can. That's a limit. So what we end up doing is we have the sum as k goes from 1 to n of f of delta sub k star times delta x. And remember, this is for delta x equal to b minus a over n. This is called the general Riemann sum. But we can actually define the definite integral by, rather than just having n, some finite number n number of intervals, let that let that n value go to infinity. So if we take the limit as n goes to infinity of the sum, k goes from 1 to n, of f of x sub k star times delta x, that gives us the integral from a to b of f of x dx, also known as the definite integral. You'll notice, again, delta x is based off of the interval from a to b. And this notation here, this integral notation, actually comes from the idea that it is a sum. So you might often hear that a definite integral is the limit of a sum, or more specifically, the limit of the Riemann sum. And this is what we mean by that. All right, enjoy!